Hi, this is TheoryStation. I'm John Duggan, and this program is the Rational Choice Modeling program. The series we're in is the Basic Formal Theory Toolkit. This is installment 19 in the series, and it's the last one. We're finally there. Last time I was talking about the one-dimensional policy choice model with voter uncertainty, and kind of worked that out. And then I decided to push that further and to endogenize the status quo. So we added a second politician, and we said, let's assume that these guys are making proposals simultaneously. Right? So there's an X1 and an X2 proposed, and then the voter just chooses the policy that's closest to them. So really the competition was between the two politicians, and we followed this idea of Nash equilibrium that we had seen before in the public good provision model. So where we ended last time, we didn't write them out, but we said, okay, we can tackle this by writing out the first order conditions for politicians 1 and 2, and that would give us 2 equations and 2 unknowns, and we could use that to try to characterize equilibria in the model. Rather than, so I want to continue down that path here, but rather than approach it at that level of generality, I want to make life easier for us, and I want to think about a version of the model where we're imposing some symmetry structure, which I'll just describe next. Okay, and I'm not going to be super formal about this, but it's symmetry across 0. Okay, so what I mean by that is, so we have our policy space, and here's 0. We have our first politician with ideal point P1. I'm going to locate politician 2 so that their ideal point is just exactly symmetric to politician 1. So it's going to be -1 times P1. Okay. I'm going to assume that the structural ideal point of the voter is just 0. And I'm going to assume that this density function is symmetric about 0. So the density for the voter's ideal, or this shock, is going to be something like that. If it were, it's not quite perfect, but okay. So in the public good provision model, we actually deduced that every equilibrium had to be symmetric, and I'm not going to try to do that here. I'm not actually sure that that's even true in this model. But I am going to look for symmetric equilibrium. So that is going to be, it's a Nash equilibrium, just like we defined before, with the added condition that person 2's equilibrium policy proposal is just exactly symmetric to person 1's. So it's equal to -1 times person 1's proposal. So if person 1's proposal is this x1 bar here, person 2's is exactly symmetric x2 bar, like so. Now, oh, sorry, I didn't mean to do that. Person 2 is proposing this, person 1 is proposing that. Now, in this model, you actually have to worry about, do there exist symmetric equilibria? Under pretty standard conditions, there will be such equilibria, and so I'm not going to try to write those out. I'm just going to, I think we can safely assume that there is one. So for example, if this density is normal or uniform, there will be an equilibrium. That's been proved. But what I want to do is try to understand what these symmetric equilibria look like. In fact, there's going to be a unique one, so that's good to know. So to get a handle on this, because we are in advance, we're looking for a symmetric equilibrium, that's going to give us a lot of leverage on this problem. So we can look for equilibria that are symmetric, and that means that the system of equations that I talked about previously simplifies quite a bit. So let me go back to that. Let me go back to the objective function of politician 1 and just take that. Okay, so the first order condition, I'm just going to do the first order condition for politician 1, and I'll argue that's all we really need to do. So, so the first order condition for 1 is the following. Now, V0 actually is going to disappear because we're assuming it's 0. Finally, I don't have to remember that anymore. So we have we're going to use the product rule. First, I'll take the derivative through this distribution function. Okay. Bear with me. And I'm missing a half here. There. Okay, so so that's the first order condition for politician 1. But remember, so in this expression, politician 1 is, they can't influence what politician 2 is doing, so politician 2 is at their equilibrium policy proposal, and this first order condition is satisfied at politician 1's optimal policy. So I'm going to put bars on all of those. Okay. But remember that we're looking for a symmetric equilibrium. So politician 2's proposal is just -1 times politician 1's. But that means that x1 bar plus x2 bar is 0. So in all of these, in these arguments here, they just cancel out. So the argument in this expression for the first order condition, the argument is just, the argument of the density is just 0. And this is also 0, and this is 0. Okay, so I mean that, obviously if we impose symmetry and just try to understand those equilibria, things are drastically simplified. Let's multiply let's multiply the left-hand side here by 2, and obviously 2 times 0 is 0, so we can just basically get rid of this and this, and we'll just add a 2 coefficient here. Now let me just rewrite all this. So we have f evaluated at 0, that is the density, times the politician's utility if their proposal is is the one that's chosen, plus 2 times, yeah, so now remember that we are imposing symmetry of the density function around 0. So if the I'm not very good at drawing symmetric looking density functions, but all right, it looks something like this. This expression here, this is not the density, this is the distribution function. So this is the probability that the shock is less than 0. All right, so in this picture, that's the area under the density. Okay, this area is f of 0. But remember, I mean, you can just see that that's half of the total area. But the total area under a density function is 1. So this f of 0 is just 1/2. Maybe I should indicate that up here. So this then is f of 0, which is just equal to 1/2 by our symmetry assumption. All right, so basically we have 2 times 1/2, so that's just 1. So we get, I'm using blue suddenly. So that's just the derivative of politician 1's utility at x1 bar. And that equals, let me just move this on the other side. That's f of 0 u1. Yeah, I won't, there's no reason to move it to the other side. Let's just do this. Okay, so so this, that system of 2 equations and 2 unknowns just reduces to, oh, one other thing here. I just noticed that I have 2 variables in here, but we know in a symmetric equilibrium, person 2's policy proposal is -1 times person 1's. Okay. So now we've reduced that system of 2 equations and 2 unknowns to 1 equation with 1 unknown, that's the x1 bar, right? And some parameters. Okay, we have this the other parameter is this density function evaluated at 0. So that's kind of encapsulating the model of uncertainty here. It turns out that all that really matters is the height of this density at 0. Okay, in a symmetric equilibrium, when you're thinking about pulling your policy away, you're concerned about the likelihood that you flip the voter's decision, which is just given by this density evaluated at 0. And that's kind of a proxy for how competitive this competition is. So with this, we have a pretty simple equation, and it's still here x1 bar. It's actually going to be a unique symmetric equilibrium policy. It's still not explicitly calculated here. If we put in the obviously we have quadratic utility for these guys. If we were to substitute in for quadratic utility, our expression then we can actually solve, and that's x1 bar is equal to minus 2p1 minus beta f of 0 times 4p1 f of 0. Okay. In a problem like this, it's always good to make sure the things look right. So in this this equilibrium, we should have politician 1 choosing x1 bar on the left of 0 and person 2 choosing their policy symmetric to the right of 0. In particular, this expression for politician 1's ideal point should be negative, okay? If you look at the numerator, actually, let me do it this way. Look at the denominator. The density at 0, I'm going to assume is strictly positive. We're multiplying that by a negative number, so the denominator here is a negative number. And in fact, I think it's going to look a little bit better if we just multiply -1 down there and do this. Okay. So now I've actually reversed that. So the denominator now is positive. And the numerator here is going to be it's going to be less than or equal to 0 if and only if the numerator 2p1 plus beta f of 0 is less than or equal to 0. Okay? In other words, let's write it like this. Right? P1 is negative, so this thing here, the right-hand side of this inequality is a positive number. And what we see is that as long as this inequality holds, say this one here, the solution to this system of equations, or now it's just one equation, the solution to this equation indeed will be something to the left of 0 and actually will give us our equilibrium policy proposal. What happens if this inequality is violated? Well, let's think about this for a second here. For example, suppose beta is big, this incentive to just have your proposal pass. Well, then this inequality is going to be violated, right? Similarly, if we fix beta and we make this competition more intense and make the density at 0 bigger, that's going to be violated. Let's look at the equilibrium policy proposals of these guys when that happens. Well, suppose we make beta big. Then you can see that as beta increases, this x1 bar, the policy proposal of politician 1 is going to increase, okay? So it's going to, so as beta increases, the policy proposal will increase. Symmetrically, politician 2's proposal decreases. When beta hits a certain level, namely when this inequality becomes an equality exactly, at that point, both of these, the competition becomes, so as beta is increasing, it becomes more important for these guys to win regardless of the policy that they're using. That's going to drive them in to 0 to try to maximize the probability that they're going to get their proposal passed. What about the density evaluated at 0? So, so as the density evaluated at 0 gets big, well, basically the same thing's going to happen. Again, these guys are going to move in as the competition becomes more intense. That is, as the likelihood of a small move flipping the outcome increases, it becomes more important for these guys to move in to try to make sure that they're not going to flip the outcome in the wrong direction. At any rate, what we see is that for some parameter values of the model, we have this exact balancing with these guys symmetrically located to the left and right of 0. As we play around with these parameters, we see that they converge inward and actually finally do get to 0 here. So you can view this as a form of a median voter theorem. It's in a sense it's the ex ante location of the voter's ideal point. So competition kind of drives these guys to sort of satisfy the voter from this ex ante perspective, that is before the realization of uncertainty. There's actually a footnote to that, though, or a qualification, which is in this model that's not actually good, because if both politicians start proposing policies that are close to 0 or actually the same, right at 0, what happens then is that the voter ends up not having any choice. So even if their ideal point is realized pretty far from 0, they're stuck with that. So there's actually an optimal amount of dispersion between these policy proposals, and the incentives of this competition will lead to under provision of that choice for the voter. And I'll stop there. This model is it's a fun one to play around with. It generates a lot of insights, and this basically wraps up the Formal Theory Toolkit. This has just been an overview of the models that I think are really the primary ones when you're doing modeling in economics and political science, especially in the area of political economy, which is what I'm focusing on. So with that, I will end the series, and in later series, I'll be going into these different models in more depth, and we'll see that they tell us even more, and I personally have found that as I get into the mathematics behind these models, it's really it's a pleasant experience, and sometimes revelatory to understand how these models work. And anyway, I'll stop there, and I will see you in a different series.